There are some terms you should be familiar with. A type 1 error is when you reject the null hypothesis when it's true. And this frequently happens because your sample isn't big enough. A type 2 error is when you accept the null hypothesis when it's false. Power calculations can be done in two ways, and as I've presented it, it's an a priori analysis, i.e. it's done before the study. And this is clearly the most appropriate way to use them because you want your sample to be big enough. Otherwise your results are meaningless. And actually, if you don't have a big enough study, your research could well be unethical. However, there are occasions when you can't do the power calculation beforehand or can't be sure that your power calculation is right, and in those cases you can do a post hoc analysis, i.e. you can put the findings from your study into the power calculation and confirm that your study was in fact suitably powered for the results and claims you make. Finally, we're going to talk about confounding variables, and here again we have a rather long explanation of the principle of confounding, and I'm going to go on and give you some examples which hopefully will explain it. A confounding variable is something that you are not measuring or not allowing for in your analysis that is in fact correlated either positively or negatively with the variables you're measuring. And two very common confounding factors are smoking. So for example, you'll all be aware of the research linking periodontal disease with heart disease. And although now there is some evidence that actually through inflammatory mediators there is actually a link, the initial research was criticised because heart disease is linked to smoking and periodontal disease is linked to smoking, and the initial studies didn't take that into account, and therefore the relationship was slower in coming to light than otherwise it would have been. Another major confounder is socio-economic status, that if you compare people from a poorer background, they are much more likely to have a disease than people from a richer background. And again, this confounding factor has to be controlled in all studies. Turning to a dental example, dental materials testing quite often use a cross-arch design or talk about fillings placed, or talk about multiple fillings placed in the same individual. And I'm going to use that latter situation to explain what I mean by this. The early sealant studies frequently would place 4 sealants in a child's mouth at age 6 when the first permanent molars erupt, and then compare that to children who had not had any sealants placed. The problem here is that each sealant is actually related to each other sealant in that child's mouth. And similarly in the control group, all 4 first permanent molars are related. So if I explain that a little bit further, if we have a really cooperative patient, all 4 sealants are likely to be easy to place and likely to be successful. Or on the other hand, if we have a patient who finds cooperation difficult, all 4 sealants are likely to be difficult to place and are therefore more likely to fail. Therefore, your results can be inflated or deflated depending on how this clustering occurs. On the other hand, in the control group, you may actually have a child who's very caries active, and that would cause the effective sealants to be inflated, or a child that's very caries resistant, and the opposite would be true. So as I said, the use of related teeth in this case in the same mouth is known as clustering, and one way to avoid it would be only to place one restoration of one sealant in each mouth, and this is the preferred method, but there are statistical methods to overcome clustering if, for reasons such as sample size, the choice is made actually to provide more than one treatment in one individual. So hopefully we have met our aims and objectives, and you now have a greater understanding of diagnostic validity and its importance and how we test and report this, diagnostic reproducibility both for continuous and categorical data, the importance of power calculations and an understanding of the mathematics behind the power calculation, although I would suggest that it's always wise to seek the help of a statistician when calculating the power of any study. And finally, that you understand that you need to consider any confounders and try to control for them in your study design. Finally, I'd like to leave you with a little bit of homework. These are 3 journals, but you can pick any journal you like, and I'd like you just to go through the trials reported in that journal and see how many of them have power calculations, how many adequately report reproducibility, if they are tests of validity, how they do that, and whether in your opinion they control for validity. Thank you very much.